the host, Don Ellison. I'm from North Carolina State University. Here for a few days. He's here for the SPAC reunion. And Don did his PhD at Catholic University in collaboration with Frank Jones at NASA Goddard Space Flight Center. Finished it quite a few years ago now, and then did a postdoc at Goddard in Maryland. You were Saclay for a time, weren't you? Something like that. Long-time professor at North Carolina State. Has worked extensively on cosmic ray acceleration theory in a number of contexts, in the heliosphere and the context of supernova remnants, which is his major focus of today's talk. He's made a number of seminal contributions to the understanding of cosmic ray acceleration, in particular in nonlinear effects, which he's going to talk about a bit today, and also magnetic field amplification. And so it's been a privilege for me to work with him on and off over the years in various contexts of cosmic ray acceleration theory. So we welcome Don and look forward to a very nice talk.
Thank you very much. So thank you, Matthew, for asking me to give a talk. And actually, I did get my PhD in Washington, D.C., but I got a master's here about 40 years ago. It only seems like 50 or 60. But so I'm going to talk about collisionless shocks particle acceleration. I've been doing this since my PhD thesis, actually. And I'm going to present this as a surprising story and talk about some of the interesting surprises along the way. I'm going to talk about first-order Fermi shock acceleration, also called diffusive shock acceleration. Here's some review papers. There's been hundreds of papers published on this over the years. But the first paper really was the famous Fermi paper in 1949, which was a response to Alfvén's solar origin model for cosmic rays. And then Fermi had his 54 paper connected to shocks. So I actually looked at these papers. Here's the original 1949 paper. And this is second-order Fermi acceleration. And here, Fermi came up with the idea that you have cosmic rays moving through interstellar medium, bouncing off of moving clouds, and they can gain energy head-on collisions, lose energy of overtaking, but there's a net gain. And this was in response to this idea that all cosmic rays originated in the sun and were trapped in the heliosphere. And apparently Fermi just thought this was absolutely ridiculous. And the story is that he attended a talk by Alfvén and he walked out and said, I can do better in 5 minutes, and wrote down this story. The only problem with this is that this was seen immediately that this would not work. And he has this even in his abstract. The difficulty is it fails to explain the way heavy ion nuclei are accelerated in cosmic rays. So this was not fast enough to overcome ionization losses for heavy elements. So a few years later, Fermi published his 1954 paper where he talks about if you somehow can trap these particles, instead of having some overtaking and some energizing collisions, all the collisions are energizing. You can overcome the difficulties associated with the shock fronts and so on. So Fermi postulated that shocks could trap particles. This is the first-order Fermi acceleration mechanism, but Fermi did not derive the famous universal power law that I want to talk about. But you should actually go on AstroPH and look up this 54 paper, because if you do, you will find that there's a errata in 1954 as well by Enrico Fermi, where apparently he forgot some n factorial factor in the derivation. And I think we should all be greatly encouraged by this. Even the great Enrico Fermi can make a boneheaded mistake like this. I mean, when I saw this, I said, okay, that's fine. So anyway, so the discovery papers for the power law, which has made this mechanism so important, are here. There are 4 independent papers all about the same time. And what you end up with is a distribution function in phase space, the power law in momentum. The power law index only depends on the compression ratio, and for strong shocks, the compression ratio is constrained to be about 4. So you have basically a model-independent power law, which is really quite amazing. If you have relativistic particles, this power law momentum is power law and energy e to the -2, and this is not wildly different from what is seen in cosmic rays. So this was the great discovery. But this is for shocks in collisionless plasma. So we have to find out what is a collisionless plasma. Well, in interstellar medium, density is low enough so particle-particle collisions are rare. And if you look at the solar wind, the collisional mean free path in the solar wind is on the order of the Sun-Earth distance. This is a problem because we see thin structures in the solar wind, in the ISM, and the scale of these thin structures is orders of magnitude smaller than the collisional mean free path. So these thin structures are possible because you have wave-particle interactions that produce a mean free path much shorter than particle-particle collisions. In turbulent magnetic fields, charged particles pitch angle scatter in the magnetic turbulence, and you get an effective mean free path, which literally can be many orders of magnitude smaller. So this is the idea that this process works in collisionless plasmas. And what, very simply, if you have a uniform magnetic field, of course, a charged particle just makes a helix, and the particle-particle collisions are extremely rare. If the particle flux is large enough, the particles distort the field, becomes turbulent, and now particle with pitch angle scatter.
Oops, sorry.
Oh.
Sorry. Hang on.
This is technology, Grace.
This is nonlinear.
I'm going to turn off the echo.
Okay, so now you have this pitch angle scattering, particle can turn around, you have an effective mean free path. And the important thing here is that this collision is nearly elastic in the frame of the magnetic field. This is a very simple idea, but very complicated plasma physics. Just to impress you, I can write down all these equations here. So you can write a dispersion relation down for this and actually solve it. I can't, but my collaborator, Andrei Bykov, can, which is fortunate for me. And the idea is that you have these complicated instabilities, but they can be described. Okay, the basic idea is that you have anisotropic cosmic ray distributions being accelerated at the shock. So this pressure gradient from the anisotropic cosmic ray distributions drives the growth of this magnetic turbulence. Simple idea, very complicated plasma physics there. Okay. But the neat thing here is that these scatterings are inelastic. Excuse me. If you have particle-particle collisions, the scatterings are inelastic. If an individual particle gains more energy than average, it immediately shares that energy with the thermal plasma, and everything goes to equilibrium. In collisionless plasma, the particles interact with the background field. One proton scatters off of basically Avogadro's number of particles tied together with a nearly frozen-in turbulent magnetic field. The scatterings are nearly elastic. An individual particle can gain energy and keep it for long times. So an individual particle can obtain much more energy than the average. And the B fields are frozen in because the conductivity is so high. You move the plasma, the magnetic field moves with the plasma. So these extremely non-equilibrium plasmas can be maintained for millions of years in the ISM. This is the classic example of the cosmic ray distribution. You do not see this in laboratory plasmas. In the laboratory, you need vast machines to produce a high energy beam for a brief instant because everything is collision dominated. You do not have shock acceleration in collision dominated shocks. So it's a collisionless process. Okay. So I'm getting back to my surprises here now that this is a surprising story. The first surprise was whether or not collisionless shocks existed at all. Before spacecraft, there's no laboratory evidence for this, and it was not certain that the collisionless plasmas work the way we just mentioned. But the first surprise is that collision shocks, in fact, do exist. They were directly observed by spacecraft. And the first spacecraft went out far enough to see the Earth's bow shock. It did, in fact, see the Earth's bow shock. This is not the first observation of it, but it is an observation of the Earth's bow shock. So they clearly do exist. And there was actually some controversy about this for, maybe Kurt, you remember that probably, until they were actually discovered. Okay. So you need low densities and turbulent magnetic fields for a collision shock, but in astrophysical settings, it's very easy to obtain supersonic speeds. Virtually everywhere you can do this. And magnetic fields are always present. Maybe we're not sure where they come from, but they certainly are always present. So the second surprise is that not only do they exist, but strong collision shocks are common in astrophysics. Here's a schematic, a cartoon of the heliosphere. There's shocks everywhere, solar flares, planetary traveling shocks, bow shocks, co-rotating interaction regions, and the termination shock way out here, which actually has been observed and passed by the Voyager spacecraft. So we have all these shocks, and many of them can be studied with spacecraft, very detailed observations of the spacecraft. But these shocks are generally very low Mach number, and they generally don't accelerate relativistic particles or thermal electrons. So here's an example of a shock that does those things. This is a supernova, Tycho supernova remnant. This is an X-ray image. This blue line here is X-ray synchrotron emission from TeV electrons. You have this bow shock right here. So this shock is is strong. You have nice global information. There's absolutely no doubt that it's producing TeV electrons, and almost no doubt that it's producing TeV protons as well in this shock. Just very quickly, there's shocks everywhere, as I mentioned. Here's a radio galaxy. We assume that there are shocks out here producing these radio lobes. And the important thing to remember, of course, is that we only see radio emission because relativistic electrons are being accelerated. So if you see radio emission in these objects, you know that acceleration is taking place. Okay, what does the Earth's bow shock look like? Well, I showed you before in case you didn't spot it. Here it is right here. Bow shock is crossed here and it's crossed here. Here's a cartoon. The spacecraft was here and the bow shock actually crossed the spacecraft. So you have a great deal of detailed information, but global information is hard to come by in these spacecraft observations. Okay, so the next surprise is that not only do you see shocks everywhere you see collision shocks, you see superthermal particles. So the question is, why is particle acceleration so general? Well, it turns out that a collisionless shock must accelerate particles to exist, to produce enough entropy to be a shock. For supercritical shocks, collision shock, it must reflect some fraction of downstream particles back upstream. These reflected particles return back across the shock as superthermal particles. This is the injection process, and they continue to be accelerated. So the third surprise is that these strong shocks always inject and accelerate superthermal particles. Now, it's been a question from the very beginning of shock acceleration, how thermal particles are actually injected into the mechanism, how to describe this. This is hard to describe. It's complex mathematically. It's hard to simulate for various reasons. But what we know from our observations is that real shocks have no problem with thermal particle injection. And I say this here because this has been controversial over the years, and I just wanted to emphasize this. But there are some nice observations. This is some work that I did with Matthew some years ago. I don't know if you remember that, Matthew, but this is a while back. And this is an observation. The dots here are observations of interplanetary shock, and then we have modeled this. And you can see that you have the thermal peak, and particles are drawn directly from the thermal peak. So you see injection taking place. This is smooth injection. It's very inefficient. This is a log scale here, so you don't inject very many particles, but you actually see it. At the quasi-parallel Earth bow shock, the one I showed you earlier, you also have observations, and the injection here is much more efficient, and you actually can calculate the efficiency in terms of the energy. And this shock puts about 25% of the solar wind RAM kinetic energy into superthermal particles. It's an efficient machine. Oh, by the way, I should have mentioned earlier, I encourage questions if you have any questions as I go along. Okay, so I have a lot of things to cover, so I'm going to keep going. There's more observations of particles being injected. This is interesting because it shows very low energy electrons being injected as interplanetary shock. And again, this injection problem has been an important problem over the years, so I showed this slide.
Stand there so you get in the picture.
Pardon?
Stand over there so you can get in the picture.
Ah, okay. Then I can't see my slide.
Oh, okay. Well, then,
Okay, there we
whatever's convenient.
So this is an interesting problem, and the way that you would really like to solve this is with a particle and cell simulation. Here's some nice work from Anatoly Spikowski of a PIC simulation where particles come in, the magnetic fields are self-generated by the particles. You move the particles, they create currents, create magnetic fields, and you move the particles in the magnetic field. So this is a self-consistent simulation. Upstream particle comes in, scatters back and forth across the shock, and gets energized. And I wanted to show you this. This is thermal leakage injection because also, Matthew, some years ago, we did this. This is 2008. This is 1994 with our Monte Carlo simulation. And of course, 20 years ago, you didn't have too many color plots and papers. So I figured, well, if we just took this and turned it and made it color, here's our upstream particle coming in, scattering off the shock. It's being energized. So it's not so different from this PIC simulation. It only took like 1% or a tenth of a percent of the computational time. Okay. So in order for this to happen, you have to have magnetic turbulence. There's always some background magnetic turbulence, we know that, but this is far too weak and normally has a narrow wavelength range. You can't explain acceleration at cosmic rays to high energies with background turbulence. In order for acceleration over a wide range, the cosmic rays, you need to produce this turbulence. So for cosmic rays to be accelerated, you need magnetic field turbulence. But the turbulence has to be self-generated by the cosmic rays. And this is done through resonant and non-resonant interactions. So the fourth surprise is that the turbulence, delta B over B, with a wide dynamic range is self-generated in shocks. Okay. And this has always been assumed to be the case. This is that same paper I showed earlier, interplanetary shock. And here you actually see this self-generated magnetic turbulence. This is weak turbulence at interplanetary shock. At this very strong supernova remnant shock, there's evidence, indirect evidence. This is direct evidence. There's indirect evidence for very strong turbulence being produced. And if you look at the radio cuts through this remnant, the red curve here is the X-ray synchrotron emission from very energetic electrons. And you see it's very sharply peaked. And the best explanation for this is that you have very, very strong magnetic fields, very energetic electrons have a very, very short lifetime. So they are accelerated, they radiate, and then they decay. So this is indirect evidence for very high magnetic fields, much higher than the background interstellar magnetic field. So the idea is that this strong magnetic field is being produced by the shock.
Question.
Yes.
Why is the X-ray with PSF compared to the X-ray? Why are the peaks shifted? They seem to be.
Which, these?
Yeah.
These
the
are
red
just,
and the black. It looks like the red peaks are a little too.
the
low.
black is the data, and the red are models to model that. And these are different
Oh,
models.
okay. So the red's is theoretical.
Yeah, red is the
No fits.
And there's a lot. This is radio, which you do not expect to be peaked because of much lower energy electrons. They don't have suffer losses.
Yeah, interior.
Okay. So my next surprise, I only have 37 more surprises. So, the next surprise is that not only do shocks accelerate particles, but there's also now clear evidence that they can be very efficient accelerators. Okay? And if they are efficient, then the injection, the process I just talked about, must be self-consistently connected to the production of the highest energy cosmic rays to conserve momentum and energy. So surprise number 5, strong collision shocks are efficient accelerators, and that means that the process becomes nonlinear. The cosmic rays have to modify the shock structure. Here's that bioshock observation I showed you, the dots of the observation. And forgetting about the models, just looking at the observations, you see that about 25% of the solar wind kinetic energy is put into superthermal particles. It doesn't look very impressive here, but if you just took the bioshock, scaled it up, made it larger, this non-thermal tail would just continue on and more energy would go into the cosmic rays. So you now have a complicated nonlinear system. So, yes.
Okay, there's one thing that's been bugging me this whole time, and it sounds really stupid. So are these collisionless shocks actually collisionless?
Yeah. Well, yes. In terms of particle-particle collisions.
So then how are they a shock then, exactly?
Exactly what you have. The question is, how do you produce the entropy in these shocks? And you do it through this wave-particle interactions. So particles turn around, they collide, but they're colliding by scattering off a background magnetic field rather than another particle. So the entropy is produced. The particle distributions are randomized by these wave-particle interactions.
So like, I guess like what I'm not so clear on is what exactly is a shock in the first place? I know that sounds really dumb, but I guess I'm not.
Well, as opposed to a sound wave where you don't produce entropy. In a shock wave, you do produce entropy. So I guess that's a simple way to say it. Maybe we can talk about that later because
I guess, okay.
It's like a sonic boom versus a sound wave. Okay, so I talked about this universal power law, which comes out of this shock acceleration process. And this is it right here. But there's one problem with this, and that is that if you try to integrate this all the way up to infinity, you find that this power law diverges. It diverges for strong shocks. What this means is that somehow you have to stop this process. You have to stop it by losing particles, or you have a finite age, or whatever. And it turns out that in strong shocks, some of the highest energy cosmic rays must escape if the acceleration is sufficient. And this has been a controversial idea over the years, but I think there's very clear evidence now that this is the case. So some fraction, in some cases, a significant fraction of energy goes into the highest energy cosmic rays, escaping cosmic rays. this is an interesting consequence of this because the escaping cosmic rays, if you shock this plasma, energetic particles escape, they carry away pressure with them. This means that the compression ratio of the shock can increase. The compression ratio increases, it means that the power law distribution gets harder, which means that you put more energy into highest energy cosmic rays, so you increase the acceleration efficiency. The more energy you lose to escaping cosmic rays, the more efficient the acceleration process becomes. It's intrinsically nonlinear. So surprise number 6, escape is an important part in strong collisional shocks. And again, there's some recent data actually showing this process at interplanetary at the Earth's bow shock. I'm not going to go through this, but there's actually direct evidence showing that particles are accelerated to the shock and then they escape upstream. And again, this has been controversial over the years. Okay. So now we talked about this magnetic turbulence. It has to be self-generated. And normally, in the past, it was assumed that this was done by resonant interactions. There's a long history here. And this was described using the quasi-linear theory. The quasi-linear theory assumes that your change in B, your delta B over B is less than 1. And this was fine for a while. And the idea was that if you just use this and you get delta B over B on the order of 1, any more energy you try to put into waves would be immediately transferred into heat. This was the idea. And we know that for the ISM, the magnetic field is less than about 10 microgauss, maybe 3 microgauss. But then these observations that I show you and others started to suggest that supernova remnants had magnetic fields at the outer shock wave, which was 10, maybe 50 times larger than the ISM field, which suggested that delta B over B somehow became much, much greater than 1. So this is a very interesting process. And this is called magnetic field amplification. And again, it's important to realize that not only is the magnetic field important for the shock acceleration process to work, the magnetic field determines the synchrotron luminosity. So whenever you see radio emission or this other stuff, the magnetic field is a critical parameter. If this is being increased by a factor of 10 or 20 or 50 by a shock, you need to know about it. You want to get this radiation understood properly. So the 7th and last surprise I have here is that the magnetic field amplification, delta B over B, can become much greater than 1, and that this is an intrinsic part of strong shocks. Okay, so now, all these things I talked about can be put together in an approximate model. I've done some work with listed collaborators here. Andre Bekoff, Herman Lee, who's the main driver on this now, and some other people that worked with over the years. We take a hydrodynamics code, VH1. We fit a nonlinear shock acceleration model to it, coming from Pasquale Blasi and co-workers. We have non-equilibrium ionization for X-ray line emission. We're going to calculate the X-ray lines that are produced. We couple the acceleration to the supernova hydrodynamics. We have magnetic field amplification, a simple model of that in this code here. We calculate the electron and ion distributions. We calculate the photon emission from radio to TeV energies. Okay? And then we've applied this to a number of supernova remnants. So let me show you some of our results. Yes?
I'm missing something here. I thought that you were trying to model collisional shocks, but you're starting with a hydro. So by definition, that's a collisional shock.
Well, that's a good question. It's a hydro code for the evolution of the supernova remnant. Okay? Basically what the hydro code assumes is that you have a density and a temperature. Right? It doesn't necessarily assume that those are determined by collisions.
So I guess what I mean is that in the hydro code, usually the width of the shock is kind of determined by kind of either numerically or by collisional processes. But in a collisional shock, the self-consistent width of the shock and the transition layer structure would be self-determined by, for example, big simulations and self-generated.
Yeah, basically, what we assume is that
what is assumed?
We take the hydro code, which has basically a discontinuous subshock, and then we couple that to this shock acceleration calculation, which tells us that we have a long-scale precursor. So we adjust the parameters of the subshock for the hydro by coupling it with the shock acceleration. So we take two independent calculations, shock acceleration, hydro, and then we couple them together. And we couple them together by basically changing the ratio of specific heats that goes into the hydro.
So in other words, you use the hydrocodone to use a skeletal structure shock,
Mhm.
and then use the whatever
Yeah,
mechanism for the particle acceleration.
yeah, the hydrocode, if you imagine it going through the ambient ISM, it needs the upstream density, the upstream temperature. But that upstream temperature and density are modified if we have shock acceleration, which is extended precursor. So we modify that, and then that feeds back to the hydrocode. Yeah, it's not totally self-consistent, obviously, but it's reasonably self-consistent. Okay, so we're going to model broadband emission. You've all seen these wonderful images here. Fermi telescope, all the way up to gamma rays, GeV, TeV, Air-Cherenkov telescopes. And the idea here, very simply, is that we have a supernova explosion. We have our last wave shock moving through the ISM. Charged particles scattered back and forth between the turbulent magnetic field. This is the shock in the frame of the shock here. Particles make nearly elastic collisions with the background plasma. They gain energy when they cross the shock. The bulk kinetic energy of the converging flows between upstream and downstream is put into individual particles. This is the basic idea. So this is what we've modeled. Again, the shock is being modeled with the hydro. The acceleration is being modeled with our shock acceleration calculation, and these are coupled together in some reasonably self-consistent way. We calculate the proton and electron distributions. These are typical distributions from very efficient shock acceleration. We have a number of parameters. Hopefully nobody will ask me how many parameters we have. But we have a number of parameters in this model.
How many?
If I had more time, I could just. Okay. No, actually, we had a number of papers on this where we describe these things in very clear detail. But there are important parameters, and that's important to remember. But these protons and electron distributions produce radiation. The only radiation produced by the protons is the pi decay here, and this is very important because for the GeV, TeV, there's always this competition between inverse Compton and pi decay to determine which is producing the radiation. But in addition, what we do in our model is we also calculate the thermal X-ray emission. And that turns out to be very important because the nonlinear shock acceleration influences the hydrodynamics, which influences the thermal X-ray emission. And this turns out to be a very important constraint. There are a lot of parameters here, but we have enough constraints that we can do meaningful things here. Okay, so this is the basic model. Again, there's a lot of references here. So we've applied this to Supernova Remnant 1713, core collapse model into a pre-supernova wind. Here's the radio, X-rays from Suzaku, Fermi, and Hess. And we actually can do a consistent fit, including the thermal X-ray emission. And our fit with the thermal X-ray emission clearly shows that the GeV-TeV is dominated by inverse Compton emission. Now, this is an important problem because, of course, what everybody assumes and more or less would like to be able to prove is that supernova remnants produce cosmic rays, cosmic ray ions. They'd like to see the smoking gun for this. If you look at this individual remnant, clearly it's producing TeV particles, but they're electrons. We see the radiation from electrons. The pi decay is down here. But the problem, or whatever, is that electrons radiate far more efficiently than protons. So even though you have a small fraction of the energy in electrons, less than 1%, 99% is in protons. The electrons are radiating much more efficiently, and that's what we're seeing. And we can determine that because we also have this thermal peak there, and I'll show you how that works. You can fit a model, if you ignore the thermal emission, you can fit a model where inverse Compton fits everything, or pi decay basically fits everything, but you cannot match the thermal X-ray emission. But the thermal X-ray emission and the pi decay scale in the same way with density. So if you increase the density, so this is pi decay here, you have to increase the thermal X-ray emission. So the bottom line is by coupling these two processes together, you can clearly show that the best fit is going to be inverse Compton. And this produces very different parameters, which of course is the reason for doing this in the first place, finding out what's going on in the supernova remnants.
Why is the thermal so much narrower than the model?
Oh, you mean this? This is observations.
I know, but your model is the black, which is narrow.
What this is Suzaku observations here.
Uh-huh.
And what Suzaku is basically showing is that there's no thermal lines. So this is the synchrotron, continuum synchrotron. What Suzaku shows is that there are no thermal X-ray emission lines. So that's the constraint. Okay.
She's asking about the shock.
I'm asking,
Why is
so
this
the
associated?
black, yeah, so what's the black prediction? Is that a black?
These are X-ray emission lines.
Okay.
Thermal X-ray emission lines from the heavy elements. Okay, so the shock heats it to millions of degrees, and then you get. Yeah, I didn't go into all the details here.
Okay.
Here's another remnant, Vela Jr., that we recently did this. And again, if you don't include this thermal constraint, then you can get a good fit either with pi and decay or inverse Compton. But once you include this thermal emission, then inverse Compton dominates the proton-proton. And here's another one, this Tycho Supernova Remnant. You have this Fermi and Veritas emission here. And this claim has been made that this is a clear case where you do have protons dominating with pi and decay. And we've looked at this remnant as well. This is from Morlino Caprioli. And we believe we have our models a little bit more self-consistent than Morlino Caprioli, where we include these nonlinear effects. And now when we include the thermal constraint, we actually end up with a composite fit here, where we have pi and decay contributing, but also a contribution from inverse Compton emission. And this is important because the total now is a relatively soft spectrum. And if you just looked at the spectrum, you might conclude, the fundamental process is producing a soft spectrum, which is not so consistent with shock acceleration. But we find that this is totally consistent with soft spectrum when you have the contribution of inverse Compton. Yes? Where do you ion come from? You have energetic protons, so that relativistic protons collide with the ambient gas. So you have proton-proton collisions. They produce pions. The pions decay to produce gamma rays.
These ions are from the Compton rays.
No, they're from the accelerated protons. Yes.
So are you saying that supernova remnants do not produce ion cosmic rays?
No, I meant to say the exact opposite, but it's important to say this again. Even though the electrons are producing the radiation, because electrons radiate more efficiently, the large majority of the cosmic ray energy is in ions. So the ions are there, they contain most of the energy, but they don't radiate efficiently. So even in this model, the 99% of the energy is in cosmic ray ions. Okay, so they are definitely producing cosmic ray ions.
But then how do you know that if you're not seeing the energy, if you're not seeing...
Okay, well that's why this one remnant was so important.
Okay.
Because in this one, you actually do clearly see the proton.
The significance.
And that's why everybody was so concerned about this.
Okay.
They wanted to get the smoking gun. Okay. Okay, so now in the few minutes I have left, I'm going to talk about the latest stuff that I'm doing, which I'm actually going to talk about some detailed calculations of magnetic field amplification. And this is work with Andrei Bykov, Sergei Osipov, and Andrei Vladimirov. And I hope all this problem with Russia doesn't go too far. It's been going on. Andrei was a PhD student of mine. He's now out in California. He joined some companies, probably making a gazillion dollars now anyway. But he's still working on this project with us. And Andrei Bykov is a longtime collaborator of mine. He's been working with him for 20 years. And as I mentioned before, all these real complicated plasma physics equations, Andrei actually knows how to do this stuff. So that is really nice. So I'm going to use a Monte Carlo model of shock acceleration. And this has been one I've been using for a long time. And as Matthew mentioned, I worked with Frank Jones on this, and Matthew worked with us together over the years. And Frank actually got a bachelor's from Rice in 1954, 60 years ago. He passed away a few years ago, unfortunately. And Frank, some of you have met Frank Jones. But anyway, he's a big guy. He's like 6'4" or so. And when he was at Rice, he was actually on the football team. So in the 50s, physics majors could be on the football team. How many physics majors do you have on the football team?
Baseball team.
Maybe baseball. Yeah. He wasn't very good at it. And also, I had some very important help from Dave Eichler early on when I first started doing this. So here, back to this magnetic field again. ISM 3 microgauss at supernova remnants estimated, and this is all indirect, but estimating magnetic fields of hundreds of microgauss. So much, much higher than the ISM field. So the question, how do you start with 3 microgauss and end up with 300 microgauss at the shock? And the idea is that this efficient shock acceleration, which efficiently puts energy into particles, also places a large fraction of the energy into amplifying the magnetic field. So you amplify the magnetic field by large factors. And this is done by instabilities. You have the resonant streaming instability, which has been known for a long time, and now you have these more recent ideas that you have these non-resonant cosmic ray current-driven instabilities. And this business, these non-resonant instabilities, was basically understood by Tony Bell. And this is Tony Bell, 2001, and Tony Bell is still working on this today. And I don't know if you noticed those first slides I put down, but Tony Bell was one of the original papers in 1977, one of the original discoverers of the power law. So not only am I still working on my PhD thesis, Tony Bell is still working on his PhD thesis after all these years. So this is, I thought, but he's making tremendous contributions here. So he came up with, first of all, what he first did in 2001, he said, okay, we have observational evidence that delta B over B is much greater than 1. Let's just assume quasi-linear theory and just let it go and let it calculate this, even though we know it's inconsistent. That was the first step. The next step that he came up with after a lot of work is that he realized that there was another instability that people had not realized was there, a short wavelength instability. Beekoff and collaborators understood after this that there's also a long wavelength instability. These are non-resonant instabilities. So what we've done is we've tried to incorporate this into this Monte Carlo model of this nonlinear acceleration process. There's a lot of people working on this. I'm not going to go through these names, but there's a lot of work on this. It's an important problem, I think. But it's a hard problem. It's a hard problem because shock acceleration is intrinsically efficient. Test particle analysis is not a good approximation. You have to have the feedback of the cosmic rays from the shock structure. Magnetic field generation is an intrinsic part of the acceleration. You cannot treat shock acceleration and magnetic field amplification separately, although this is the way it's normally done. Quasi-linear theory is our most important tool, but it clearly is not good if it assumes delta B over B is less than 1, so that's a problem. We have information from heliospheric shocks, all the in situ observations, but these are mainly small, low Mach number shocks, and you generally don't see the production of relativistic particles. So you don't see Bell's instability in heliospheric shocks. You would like to do this with particle and cell simulations, but the length scales that are required are still well beyond what's possible with PIC simulations. The Bell's instability is generated by the highest energy cosmic rays, well out the precursor. PIC simulations have a long time before they were able to do that. So to cover the entire dynamic range, you have to have approximate methods. And the approximate method I'm going to talk about is the Monte Carlo technique. The basic elements is that we assume particle transport. Basically, we assume pitch angle scattering that can be described with a mean free path, a function of position and momentum. And this assumption, rather than calculating this from first principles as particle and cell simulations do, by making this assumption, it allows us to have a large dynamic range. We can treat anisotropic distributions in the Monte Carlo model, no problem. We include the back reaction of the cosmic rays on the shock structure. We also have thermal particle injection is built into the model, so once we assume the mean free path, we describe injection self-consistently. And we also include the effects of the free escape boundary particles leaving at the upstream free escape boundary. And this is still a very active area and is just starting to come into play, calculating the turbulence of these escaping particles. People have started doing that. We have not yet done that in our models. Okay. Of course, there's a lot of approximations. It's intrinsic steady state. We just do a plane shock where we have the finite shock is determined by a free escape boundary, parallel geometry. Oblique shocks, of course, have been done. Matthew and E.J. Summerlin have done some work on relativistic shocks, oblique shocks. And you have to beware that these analytic descriptions of these instabilities are extremely complicated, but even in the complication, there's a lot of subtle approximations that you have to watch out for. The Monte Carlo technique, I believe, fills a middle ground. It's faster and can cover far greater dynamic range than more fundamental PIC simulations. And it avoids the diffusion approximation, which is really a problem for the faster semi-analytic techniques. Okay. So we have this process, we have thermal leaking injection, acceleration efficiency, shock structure. All of this is determined by what we assume for the diffusion coefficient, which is calculated by the magnetic field. So this is all connected together, all these processes. The instabilities are driven by the constant current and pressure gradient, and these are determined by the Monte Carlo simulation. So you have to do this iteratively. So we start with a unmodified shock at a given flow speed, a given compression ratio. We start with a uniform ISM field, Kolmogorov background turbulence. We run the simulation, we inject particles, we move them through the shock, calculate the momentum and energy fluxes, including contribution from the waves, calculate the pressure gradient, cosmic ray current, and the anisotropic distributions. We calculate all the fluxes, including the escaping energy flux. If the fluxes are not conserved, we redo everything. We keep doing this iteration until we come up with a structure, magnetic field turbulence that conserves momentum and energy. So this is, of course, I'm going through this very quickly. It's a complicated process, but I think we put this all together in a reasonably self-consistent way. Okay. This is very recent work. We just submitted this. This is the first calculation, I believe, where we have magnetic field identification, including all three instabilities, resonant and non-resonant. And again, in principle, this is done with PIC simulations, but there's still too small for this. We use the analytic expressions from Bell and Beekoff to generate delta B. Two very important results is that we do not have to assume that this turbulence is alpha-plane waves. It's a nice generalization. And we managed to overcome the quasi-linear problem because in every one iteration, in every particular iteration, delta B over B is less than 1. We then modify the shock structure and go to the next iteration. So we can attain delta B over B much greater than 1 without violating the quasi-linear approximation. And again, I'm going to finish up pretty quickly here. Again, this is a complicated process. We have these, this plasma physics in a complicated Monte Carlo model. We have to put this all together and we have to iterate it. The bottom line here is that we have complicated equations and a complicated model, but all the required information, once we make our approximations, is there. So we can do this, we can put it together, and we can obtain a self-consistent solution. And that's where we stand now, and I don't want to spend too much time on these details, but let me just say a little bit on these instabilities. Bell's instability is the fastest growing mode for short wavelength turbulence, shorter than the gyro radius. So you have these high energy cosmic rays, they have a gyro radius, large gyro radius, and the background magnetic field, which is almost uniform. As they gyrate through this background magnetic turbulence, the current produces these short wave turbulence. That's what Bell discovered with his instability. So Bell's instability produces waves with scales shorter than the particle gyro radius. Okay? What Beekoff realized is that the presence of this turbulence with scales shorter than the gyro radius enhances the growth of waves with scales larger than the cosmic ray gyro radius. So we have all this small scale background turbulence, we run the cosmic rays through it, it produces turbulence on large scales. So this will produce scattering with a mean free path and a certain momentum dependence. So in the presence of short scale Bell type turbulence, long wavelength modes are amplified. This complicated problem, but the bottom line here is that if you can produce turbulence with long wavelengths, in fact, wavelengths greater than the particle gyro radius, this impacts the maximum energy you can generate in a shock. And this is one of the critical things we'd like to understand from this. What maximum energy can a shock produce? We have cosmic rays that are up above 10 to the 20th electron volts. How do we produce those cosmic rays? So here's our shock structure. Flow speed is smoothed by the back pressure of the cosmic rays. Flow coming in, subshock, shock plasma here. We have different positions. This is the subshock, this is the precursor. So far upstream, we have a distribution like this. As we get closer to the shock, we get a distribution like this. This is what comes out of the Monte Carlo. With these distributions, we can produce the turbulence at these various positions, blue, green, red, and black. The turbulence is used to produce the diffusion coefficient, but the diffusion coefficient is needed to produce the scattering to begin with, so we have this iterative process where we iterate between these processes. All the time modifying the structure, searching for conservation, momentum, and energy. Here are the most recent results where we have the self-consistent shock structure, particle distribution function downstream for the shock, and here's our diffusion coefficient. And if you know what you expect this to be bone-like, you see that this is very clearly not bone-like in this model. Okay. One interesting thing that we find is that even though the turbulence is dependent on the details that we assume, the final particle distributions are not very sensitive to the assumptions that we make. And I think the basic idea here is that since this is so efficient, there's not much you can do about it. If you're putting 75% of the energy into the highest energy cosmic rays, you can't modify that very much. So this is relatively insensitive to the details. Okay. Here's some more details. This is the turbulence that we produce. So this is very long scales here. So the very energetic cosmic rays produce this very long scale turbulence. And without cascading, we get these peak structures in the turbulence, which turns out to be quite interesting. And Beekoff has suggested that these peaks in the turbulence at very longest wavelengths could explain these X-ray stripes that are seen in the Tycho Supernova Remnant. And what we find is that when we have no cascade, cascade means that you take the longest wavelength turbulence and it cascades into shorter wavelengths. So you have long wavelengths turbulence here, and it cascades into shorter wavelengths. With cascade, you eliminate these peaks, which would be a problem for explaining these stripes in Tycho Supernova. Okay, a lot of details here, and I'm essentially finished. So my surprises, collision shocks do exist. Shocks are common. Collision shocks always inject and accelerate some particles. Turbulence is self-generated in shocks. Not only do the shocks accelerate particles, they are efficient accelerators. Upstream escape is an important process in this whole business. And magnetic field amplification may be an intrinsic part of shock acceleration in strong shocks. So this process is complicated, but with the complications come meaningful constraints in the observations. The idea that we were able to explain some of these supernova observations by adding complications, I think was quite interesting. And I think that the surprises are not over yet, even after more than 35 years of doing this work. That's it. Thank you.
Questions? Is there a time scale associated with the development of the magnetic turbulence as the remnant encounters whatever fields, and then you have your cosmic rays being accelerated, and then you're generating that turbulence and getting more acceleration?
Yes, you certainly, it takes time to generate, it takes time to accelerate the particles, and it takes time to generate the turbulence. And that's an important thing, because if you produce turbulence very far upstream, it starts to grow, but then it's being swept towards the shock into more dense regions, and it's compressed and so on. So that is included.
So what are those timescales? Like, how long does it take for that to happen? And what does it depend on?
It depends on the growth rates. I went through this very, very rapidly, but we calculate the growth rates for the, it only took us like 3 years to generate these plots, so I assume that you can understand them in 2 minutes. So, we do calculate the growth rates, and this is all included. So we have the growth rates at any position, we have the convection of that turbulence, out of that position, and so on. And this is inverse seconds here. Yes?
If you have a pre-existing magnetic field, though, you can get a much cleaner shock with a lot less turbulence and a lot less upstream waves. What we call the quasi-perpendicular shocks versus the quasi-parallel shocks. And, I mean, can you almost see in that Tycho picture, it looks like there's some areas where it might be quasi-parallel and some areas where it might be quasi-perpendicular.
Well, the geometry issue is also another important one, which I didn't mention, the idea of parallel versus perpendicular shocks. And certainly if you have a perpendicular magnetic field where the magnetic field is perpendicular to shock normal, you can get a very clean, discontinuous shock. The problem is that you can't produce cosmic rays over a wide dynamic range with those shocks. You have to have turbulence. And once you get the turbulence, even if you start off with a quasi-perpendicular shock, the turbulence basically destroys the geometry. So it becomes...
The spell shocks, our nearest example.
Yeah,
where we get those sample
Yeah.
turbulence.
Same bow shock in different areas. It's quasi-parallel versus quasi-perpendicular.
The remnant that I didn't show is SN1006, where there's very clear difference on two sides versus the other two sides, which may very well be the case of the geometry of the this field.
Kurt, you had a question?
Now, when you write delta V over V,
Pardon?
when you write delta V over V, when you get about 25,
Right.
what does it mean? I mean, it sounds like a statistical joke, that the fluctuations of V are larger than V.
Right. It makes no sense to say that the fluctuations can be larger than V, right? It basically means that what the problem is the B, not the delta V. Now, if you have a magnetic field which is highly turbulent, you basically are scaling it to some constant B field, basically. So we're not, right. You have a magnetic field and it becomes highly turbulent, so you can do a root mean square of what the magnetic field is.
So Don, can you back up to your first power spectrum slide from the magnetic field? That one there. So the generic character on the upper right is blue to black, is you're sampling the larger scales in blue,
Right.
and the nearest scales to the shock, and you're just moving your scales as you go closer to the shock. You get the smaller scales when you sample.
Yeah, this
Therefore,
is
the larger
large scale, this is small scale.
Right.
And the large scales are generated very far upstream.
Yeah.
But
So
Kurt, I hope I answered
mapping.
your question, but we characterize it as delta V over V, but we never use that parameter in the model. We calculate the turbulence.
I just wanted to talk about it. I was leaning towards the V in the denominator being a magnetic field that you started with.
Right, you can certainly say that. What if you start off with 3 microgauss, and then you do your calculation, you find that the turbulent magnetic field, the root mean square is 300 microgauss, then you could write a delta V over V as 100, but it wouldn't mean anything as such.
Okay, let's thank Don again. And, Don's around today and on and off sporadically the next couple of days. And questions, you can come by.